Okay, so for today's topic, it's going to be integration tables. Okay, and this is something that you can find in just about any textbook on calculus. All right, so this textbook I happen to have handy. It's actually a pretty old textbook, but you can find things like this in modern textbooks. Okay, it's in the appendix and it says table of integrals, and there are some basic forms. I notice right there that's integration by parts. And just along here, I see a lot of the integrals that we encounter uh, frequently. Okay, but it has, if you keep looking, these more exotic forms, right? And they're grouped according to their appearance. Like if it says it has root a squared plus u squared in it, then we get a whole series of integrals that involve that expression. Okay, so now I could show you this more and more and more. Let me see, how many different integrals are there? There are 120 total forms of integration on this table. Now, that's what you get in integration tables, okay? You can just look up answers to, not any problem that you could ever find, because actually some integrals involve special functions that you don't know about yet, and that they probably won't appear in an integration table in a calculus textbook, but you can find a lot of stuff that you would encounter in calculus 2 in a table of integration, okay? All right. Now, so you might wonder then, well, if you can look up the answers to these things some of the times, why do we learn all these methods? Like we learn integration by parts and we learn trig substitution and on and on and on. And I guess the answer I can give you to that, I can give you three things. That one, it's kind of like learning arithmetic. So we have calculators, obviously, but we still believe that if you're going to do something highly technical and quantitative, that you should still learn arithmetic at some point, even though you'll probably rely on a calculator, okay, eventually. So we still believe you should learn how to do arithmetic so you have the concept of what's happening when you press these buttons, all right? So that's one answer. Integration by parts is kind of like that. Trig substitution is kind of like that. That even though you might take some shortcuts later on, we still think that you should learn how it works. Now, I don't think you should spend years learning how to do integration by parts. I think you should spend like 2 days on it and learn it and be done with it, all right? So if you're like spending weeks and weeks and weeks struggling learning integration by parts and trig substitution, that's not really how it's supposed to go. All right, we think it's something that you should learn in a matter of hours, really. Okay. All right, so that's my first answer. Second answer is when you're at university, what you experience is more akin to education rather than training. If you were being trained to do something, you would be told the shortest and most efficient way to get it done every time without any complicating information, all right? But education is broader. Education, I guess, we're teaching you how the thought process works rather than simply what the bottom line is. So say you don't like any of those answers as to why we learn all these integration forms when you can just perhaps look them up on tables or use calculators to do them. If you really do something like in a hard science like physics or an engineering discipline like mechanical or aerospace or electrical engineering, then you'll encounter some problems that might very well take an abstract form and require something like a trig. See, there's a trig substitution right here. This problem is that we have a wire carrying a current, all right? And we want to calculate the magnetic field at a certain point away from the wire, all right? And these numbers aren't definite. It's an abstract problem. We're just in this book right here, when we learn this kind of thing, we're trying to get a feel for how would this work in every situation, all right? And to do that, to do all the mathematics it takes to figure out what the magnetic field is going to be like, because the current in the wire, we end up doing something like a trig substitution. So, I mean, unless you learn how to do that when you take calculus, then when you take, say, physics, and you'll get lost in the explanation for how something like this ultimately works. So that's another reason why we learn things like integration by parts and trig substitution, is because you might need them in their abstract form to describe a general situation. All right? Okay. So those are my 3 answers to why we learn all these techniques of integration when we can, in fact, for your basic problem, just look up the answer or just use a calculator to do it. You might not like any of my answers for why we still learn this stuff, but that's okay. I can live with that. I think those are good answers. All right. So let's see. Let's try this first problem. I thought the way I would do this is, rather than sift through that entire table of integrals, I thought I would just show you some forms that you'll encounter on, say, a quiz or something like that, and that way that you'll be familiar with them if you see them again, or you can refer to the video. So let's say that on that table I showed you in my other book, there might be a series of integrals of the form a plus bu, okay? And this is one of them that I find, u squared over a plus bu du, and then it gives us this answer, all right? So this problem is like that. Here the variable is u, and a is considered a constant, and so is b, okay? So I can correspond this to this by just saying, well, it's, that formula over there. The variable is x instead of u, but the constant a is 5, and the constant b is 1, all right? So, well, that would mean that this is our answer. So 1 over 2b to the third is 1 over 2, okay? A plus bu squared, so that's going to be 5 plus x squared, okay? Minus 4 times a, so that's going to be minus 20, times a plus bu, so that's going to be 5 plus x again. And then 2a squared, so a is 5, so that's going to be plus 50, okay? And then natural log of a plus bu, so that's going to be 5 plus x again. All right, so it looks like I got all that, and then it's just plus c for our constant of integration. All right, so there are lots of ways you could rewrite this. There's lots of algebra in there and so on. You could do what you want. For WebAssign, I would imagine if that's what you use, you probably type this in and it would accept it just fine, okay? If you, say, square that out and multiply that 20 in there, and then, combine some like terms and so on, and multiply the half, you could get this also. We could get, let me see, 1/2, and then say I square that out, I do 20, like all in there, multiply, I'll get x squared minus 10x minus 75. Okay, and then say I distribute the half over here because I see I got a 50, then I could say 25 natural log 5 plus x. Okay, so that's something that you could do if you needed to do a little bit of simplifying. All right, now for WebAssign, who knows? I guess I think it would accept just about any answer that was remotely correct. But I'll give you either of these. Okay, so I think one of these will work. Okay, all right. So let's try the next one. All right. So another form that you might see in a table is root a squared minus u squared. Okay. And say that this is my problem, I might find that one to be the one that corresponds to this. So this, when I was looking in my book earlier, that book I showed you that had the table of integrals, this is the one I found that corresponds to this problem, and I think you can see why that is, okay? U is the variable, and then a is a constant. So that's going to be a squared right there, and that means that a is equal to 1. Okay, so I'm going to get then negative 1 over a squared, so that's going to be 1. U, well, u is just a variable. Here my variable is x, okay? So I'm going to get negative 1 over x, and then times root a squared minus u squared. Well, that's 1 minus x squared. Plus c. Well, so that wasn't so bad, right? You know, it took me a minute to find that one on my table, but it was there, and it's pretty easy to make it match up to this. All right? Okay, as far as simplifying, I don't see any other options for simplifying that. I guess you could write this as 1 fraction and put negative root 1 minus x squared over x, but again, I think WebAssign would take this or some other form of it where the fractions combined, okay? All right, so let's do one that might take a little bit more work to get it to play out the right way. Okay, so let's take this one. I also see on my table form a squared plus u squared. Okay, and for this problem, I don't see, like when I was looking at my table earlier, I don't see anything that's exactly like this. Okay, it says 42 plus 25x squared. So this is a squared, where again a is a constant, plus u squared, and u is the variable. It doesn't say that we can have a coefficient there on the variable. All right, so I guess my concern is over this 25 right here. So let's do this. As we sometimes do in math, when we have a formula and our problem doesn't quite fit what the formula specifies, then we do a little work to make them match, all right? So suppose I could say, well, I'll factor out the 25. 25 times, let's see, I don't know what 42 over 25 is. That would be 1.68, so we'll get 1.68 plus x squared. Okay, so that's what's under the root. 25 times 1.68 times, or 1.68 plus x squared. That's if I factor out 25. So you might imagine that under this root is a 25, and this expression with the sum 1.68 plus x squared. So how about, so I'll take root 25 as a constant out of this whole thing. Okay, so root 25 is 5. That's going to exit this root and leave the rest of this behind. So let's say x squared root 1.68 plus x squared dx. Okay, so now that I can see as a fit to this. It's a squared, where again a is a constant, plus the variable x squared. Okay, now remember, when you look at this, a is a constant, u is the variable. All right, so let's do like this. Let's put some notes here. U is equal to x. All right, the variable here is x instead of u. And then a squared, we're going to have to say that's 1.68. Okay? All right, that's how it's going to need to be. So here's what we'll get. I want 5 times the answer to this. All right? So that's going to look like this. 5 times, all right, what's it say? U over 8. So that's going to be x over 8 times a squared plus 2u squared. So that's going to be, that's a squared right there, 1.68. 1.68 plus 2x squared root 1.68 plus x squared. Okay, so that's this part right here, minus a to the 4th power. Well, if that's a squared, if that's 1.68 to be a squared, I need to square that to get the 4th power. So if I take 1.68 squared, I'll get 2. It's not a nice number, but it's the number I get, 2.8224. Okay, so I'm going to get next 2.8224 over 8, and then natural log x plus root 1.68 plus x squared. And then let's squeeze it in there. You know it's there, plus c, the constant of integration. That looks ugly. That's not my best handwriting. But that is definitely not my best handwriting. But there's like 5 times all this and then plus c. Oh, it's painful to write that so sloppy, but can you give it to me? All right. So here's what happens. I'll multiply by 5 and all the way through here, and I'll just divide out the 8 also. All right, that's what I'll do. So let's see. That's going to be 0.625 right here. That's 5/8. So let's do 0.625 x 1.68 plus 2x squared. All right, root 1.68 plus x squared. And here, let me work this out. I'm going to take this, I'm going to divide by 8, and I'm going to multiply by 5. Okay? So what was that number? 2.8224. I'm going to divide by 8, and then I'm going to multiply by 5, and I'm going to get 1.764. So this will be minus 1.764. Natural log, absolute value, x plus root 1.68 plus x squared. Okay, then plus c. I feel much better about that. Okay, now this one I was concerned about when y'all are using WebAssign, how picky it would be. And I actually did work this one out earlier, and I put it in just to make sure that it would accept something like this. Just, I wasn't that worried about it, but I thought I'll feel better if I check and make sure that it works out. Okay, so that is based on this 5, this integral, with that answer. All right. Okay, so now you got that one. Let's look at one more. Okay, cosine to the 4th power u du. So what about this one? These mean the same thing. This is the way that I might see it in my table of integral, but I've noticed WebAssign often puts the power intentionally on the outside just to make it more obvious. These mean the same thing, of course. If I put the 4 here, it means the same thing if I put the 4 like that. That's the order of operations for the exponent, okay? You would do this as cosine of that angle, you calculate that, and then you raise that number to the 4th power. So I've got my answer here. I guess the problem is, here the variable is u, and here the variable is x, and the difference is it doesn't say cosine of a constant a times the variable u, it just says cosine of u. I've got cosine of some constant 3 times x. So I think what we should do to make this be compatible with that is a u substitution, okay? Just because otherwise that 3's in the way right there. This formula doesn't make room for there to be a constant like that. So I'll say u is going to be 3x, and that would make du equal to 3 dx. And I would like to completely substitute this in terms of the variable u. So to substitute the dx, I'll say du over 3 is equal to dx. And that's always how we use u substitution, right? That's how we do it. So, okay, if I do that, I'm going to get 1/3, because of that, the du over 3, cosine 4th power u du. Okay, so the u substitution introduced this factor of 1/3, but otherwise it gave me the form of my integral that I've got my answer to, okay? So I just need to take this and multiply it by 1/3, okay? So here it goes. I'm going to get 1/3 times 12u, okay? Because now, u is the variable in both my formula and the problem I'm doing at this point. 12u plus 8 sine 2u plus sine 4u plus c. Okay. All right. There you go. Right onto that formula. Now, I guess from here, though, oh, whoops. I forgot about the 1 over 32. Okay. So let's do 1 over 32. And I actually need to multiply that by a third, right? It's 1/3 times the result of this integral, and I put the result of the integral in the brackets. Okay, so let's do this. I'll multiply together, and I'll replace the u with 3x. So I'll get this. I'll get 1 over 96. 12u, that's going to be 36x because u is 3x, plus 8 sine of 6x. Okay, because again, u is equal to 3x. Plus sine 4u, so that's going to be 12x. Okay, plus c. So there's another one that, I was curious earlier today about if WebAssign was real picky with these problems where we get the integral from a table, all right? And I did try this out just like that, and it worked fine for a similar problem. Okay, so I think you're okay with this. Now, I've showed you every type of integral that you'll see in the assignment. If you're looking at this at some point in the future, when I'm making this video, this is intended for an assignment on WebAssign. So I've showed you all of the forms that you're going to encounter except 2, all right? And so let me leave you with those. I think that if you saw how I used the ones so far, if you saw something like 1 over 1 plus e to the 5x power, that would be like this. Again, a is a constant, u is the variable, all right? Oh, whoops, I meant to write that as a u, because u is the variable, all right? And this one, maybe if you saw something like u squared natural log of u, or u to the 3rd power natural log of u, something like that. Here, n is a constant, it's an exponent right there, and u is the variable, all right? So I'll leave you with those, and with those 2 plus the ones I showed you, that's every form of integration that you see in the remainder of the assignment. The real table, I can't remember what the number was. How many did I say it had? Like 120 something. Yeah, 120 forms of integration. Well, I think I've showed you like, I don't know, 5 or 6 in this video. All right. Okay, so there's way more, but you get a feel for how they work if you can see the ones I showed you here.